Good morning, class. It is Tuesday, March 31st. Welcome to the next week. Welcome to another 30 days at least of social distancing. I hope you're all playing your part. Just a reminder that lab number 5 is due today by 12 noon. So if you haven't submitted it yet, you might want to pause the video and make sure you have that uploaded. Today's lecture, we're going to look at what's called measures of position, another way of looking at statistics. And essentially, when you take a look at data values in a set, when you, in a sense, put them in order, we're now ranking them in order from least to greatest based on where they place in the data set. So the outline for today's lecture, we'll be looking at percentiles and quartiles. They have the same ending, so that they are related. We'll look at z-scores and what's called the empirical rule. So let's start with percentiles, and then we will look at quartiles shortly. So let's first start off with the definition of what a percentile is. You've probably heard the term before when you get results back from standardized tests. You'll see that your score is a percentile. So first, the definition is the kth percentile. So that could be the 50th percentile, the 90th percentile. The kth percentile is a value such that k% of the data are less than or equal to a particular value in the data set. All right, so k% of the data is less than or equal to the particular value that is that percentile. So the notation for it is P sub k, which will just stand for the kth percentile. And one note about what it is, it's a measure of placement or rank, not an actual score. Okay, it's not an actual score, but a placement. All right, so that last slide corresponds to the first question on your NTS. Now the second question corresponds to this example. So suppose that your percentile for a test is P90. What does this mean? So the first thing that it means is simply this: your score is the 90th percentile. Easy enough. Second thing, the interpretation of that is that 90% of all scores or all people that took the test scored less than or equal to whatever your score is. All right, so 90% of all scores are less than or equal to your score. So it sounds like overall you did pretty good in terms of rank. That also means that 10% of test takers did better than you. All right. Something else that it means, it does not mean that you scored a 90. So 90th percentile is not a grade of 90. And of course, with that, obviously, number 4 follows from number 3. That P90 doesn't give you any information about your actual raw score itself. It just tells you or gives you an indication of your ranking or your placement compared to everybody else that took that test. Here's another example. All right, so suppose that Jennifer received the results of her SAT exam. Suppose that her SAT math score is 600, which places her in the 74th percentile. How can we interpret the meaning of the 74th percentile? So just like the last example, the first thing we would say is that 74% of all SAT math scores or test takers are less than or equal to Jen's score. So 74% of all those test takers got 600 or less on their SAT math score. And of course, the reverse of that is also true. How many scored higher? 26% of the scores are better than Jen's. And of course, the third thing that we just say here is that we know that our score is 600. So obviously, a 74th percentile is not a score of 74. It's a rank. All right, it's a ranking. The next part of percentiles are quartiles. So when you think of percentiles going from probably 0 to 100, you figure quartiles are probably at the quarter marks of that range. So of course we'll be talking about the 25th percentile, the 50th percentile, and the 75th percentile are the 3 common quartiles that we use in statistics. So remember that we learned something about these before. Remember we were drawing box and whisker plots. We needed the quartiles as part of the 5-number summary to plot a box plot. So Q1, Q2, and Q3 are numbers that we got to plot the box plot. And you also know that they're called quartiles, but also they are special percentiles. They're special percentiles. All right, now specifically, first one. So the first quartile, remember the first quartile was more towards the left, so it corresponds to like the bottom 25% of your data. Okay, so it divides the lower 1/4 of your data from the upper 3/4 of the data. So remember what quartiles do? Remember how we drew a number line and we split it into 4? And the first fourth was Q1. So that's exactly what this is saying. It takes the first 1/4 of that line and separates it from the rest. So Q1 can also be called P25, the 25th percentile, where 25% of the data are less, all right, than that particular value. Q2, remember, is the median, all right, and that's right in the dead center of the data set. So when you think of the number line, when you split it in half, you're splitting the bottom 50% from the upper 50%. Okay? So another way of describing that is that that's the place where 50% of the data are less than or equal to whatever number that is. And of course, Q3, when you figure the third quarter, will divide the lower 3/4 of the data from the upper 1/4. Okay? And we call that the 75th percentile because remember, 3/4 is 75%. Just like 1/4, Q1, is 25%. Okay. And fourthly, the IQR, since you are subtracting Q3 and Q1, which are percentiles, the interpretation of IQR is, well, of course, it's the difference of Q3 and Q1, but when you subtract two numbers, you find their difference, but also we call that difference the range. So the range is the difference between two numbers. So Q3 minus Q1 is the range of the middle 50% of the data. All right? So I hope that makes sense. I wish I had a picture here to show you. But remember, Q1 is the 25th percentile. Q3 is the 75th percentile. So think of what's the difference between 25 and 75? It's 50. So therefore, when you think of subtracting those, the difference is 50%, and it's really the middle of the data. Okay? Maybe go back and look at box plots and look at where Q1 and Q3 are. They make up the box, don't forget. All right? Q1 and Q3 make up the box, and then you have the whiskers. So the box is really what this is describing. Okay? So the box is being described here in terms of percentile. The box of a box plot is the middle 50% of your data. All right, this is a problem that is on your NTS. So let's take a look at it. We're going to be doing parts A and B only. There's a C and a D part there, but we don't need it. So 17, violent crimes include rape, robbery, assault, and homicide. What an exciting problem. The following is a summary of the violent crime rate. So it's the number of violent crimes per 100,000 people for all of the United States in 2012. So these are the quartiles. A, provide an interpretation of these results, and B, determine and interpret the IQR. So for first part of A here. So remember, Q1 is the 25th percentile. So remember, percentile means the percentage that is less than or equal to that particular value. So here we would say the first quartile is 25% of violent crimes in the USA are less than or equal to this number, the 252.4. Now, more specifically, you could say less than or equal to 252.4, but it's better to say per 100,000 people because of this rule right here in parentheses. So the numbers that you see here are per or for every 100,000 people. All right? So now, how would you interpret Q2, the 50th percentile, the median value, right? That you would say that 50% is less than or equal to this value. But more specifically, 50% or less than or equal to that 338.8 out of every 100,000 people. Similarly, the Q3, or the 75th percentile, is the percentage less than or equal to 454.5 per 100,000 people. Okay? Interpret the IQR. So now let's calculate that. So the IQR is Q3 minus Q1. So you take the two numbers, subtract them, and you get 202.1. So now just take the definition of IQR that I gave you and just copy and paste it and plug this number in. Okay? So you would say that the IQR represents the range of the middle 50% of data. Now, in this case, the data is the number of violent crimes per 100,000. So it's the middle 50% of violent crimes is 202.1 per 100,000 people. Okay? And that's it for this example. All right, now here we go with part 2, z-scores. Now you probably noticed that I'm doing the presentation a little differently this time, just doing everything in PowerPoint rather than writing it. It's going to make for a much shorter video. So of course, you're probably going to need to pause the video to kind of catch up to me. Okay? So just make sure you do that, pause, copy what you need to do, and go. So number 2 here, z-scores are another type of measure of position of the data. Okay, so where in the data set do the values place? So we just looked at describing data placement in terms of percentages. So now we're going to go back to what we learned last week about means and standard deviation. Mean and standard deviation are used a lot, so make sure that you're caught up with that and you're familiar with mean and standard deviation. You're going to see a lot of that throughout the rest of the semester. All right, so now a z-score. So this is the gist of it, and then number 2 will be the definition. And this is the next question on the NTS about defining a z-score. So number 1, this is not the definition, but it's a little bit of a basic description. So what are z-scores used for? They're used to compare data values within a data set, or you can compare data values between multiple data sets. So you might have a data set for one semester of students and a data set for a different semester of different students for the same statistics class. I notice a lot of you are in psychology. When you get into psychology, you're going to be comparing groups as well in psychological studies. You're going to have control groups and you're going to have non-control groups. So control groups typically get placebos. They don't get the actual medication or treatment that's given. But then you have the treatment group, the non-placebo group, that receives actual treatment. And then what you want to do is you want to compare it to see if there's a difference between the two groups and just really determine if the medication or whatever psychological treatment might be applied is, making any difference. So that's the whole point here with z-scores, is that this really makes it possible to compare multiple data sets of different things. It's great. And it's going to be in relation to their means and their standard deviations. So again, you have to know mean and standard deviation. Here's the definition. So the z-score represents the distance that a data value is from the mean in terms of the number of standard deviations. Now, this might sound like the definition of standard deviation, and it's an alternative form of the definition of standard deviation where we're looking at that particular distance from the middle, from the mean, that a data value falls, and we're measuring it in terms of the standard deviation, that average distance. Remember, standard deviation is the average distance from the middle. So a z-score will be a number that is given to every single data value. All right, it's given to every single data value to determine how far it is in terms of the standard deviation. Plenty of examples to follow. All right, so let's talk about the types of z-scores that we're going to encounter. So first, a positive z-score will indicate that a particular data value is above average. If it's a negative z-score, the data value is below average. And what do you think a z-score of 0 means? Positive is above average, negative is below average, 0 would be, I hope you guessed, the average itself. All right, so the z-score of 0 is the mean itself, the average. For example, suppose we have these two z-scores. How would you interpret these? So the first one, we would say, for positive 1.24, we would say whatever data value that represents, that value is 1.24 standard deviations above the mean. It's above the mean because it's positive. I remember the z-score, all right, is in terms of the number of standard deviations. So whenever you see a z-score, all right, it's like when you have like distance, you have like 2 feet, 3 feet, 4 feet, miles, inches. When you have a z-score, it's standard deviations. So 1 standard deviation, 2 standard deviation. So make sure you get used to saying 1.24 standard deviations. The second one is a data value which is 2.31 standard deviations from the mean, but in this case, because it's negative, it's below the mean. It's below average. All right, so that's just in general how we think about z-scores. Here is the second example. Now, this is also on your NTS. There's where you're asked to define z-scores and include the two examples that follow. One is typed, one is handwritten. So this one right here at the bottom of the screen is the typed example. Here's the handwritten example. So suppose that, now look right here, we have, remember this Greek letter mu? Mu equals 100 and sigma equals 5. Remember, what's the meaning of these? Remember, mu is the population mean. So in this example, I'm given a population type problem. So the population mean is 100 and the standard deviation is 5. Now here's what we do typically in statistics. Remember, we're very interested in taking a look at distance. All right, so we look at the mean as our center. So 100 would be the center of that line. And we also label that as with an X, which represents our data set. So we put 100 in the middle. And remember that standard deviation acts as distance from that middle. So easy enough, if the distance is 5, you're going to go 5 to the left and 5 to the right and establish a little bit of a range there. So if you go 5 below and 5 above, it's 95 and 105. But notice I left a little room there, okay? So we're going to be doing a little bit more in just a minute with some more values. One thing I want to show you next now to kind of relate this to z-scores. So remember, with z-scores, the mean has a z-score of 0, okay? So what I would do next is underneath this line, I'm going to draw one more line, and we're going to call it the z-axis. So the 100 is the mean. That's going to have a value of 0, or z equals 0. Okay, now let me explain the rest of it here. So on the number line, you're going to put 0 where 100 is. All right, notice how they line up. Because 0, remember, represents the mean by definition. But now I have -1 and +1 here for the z-score for 105 and -1 for the z-score for 95. Why is it -1 and +1? Because what did I do? I started at 100 and I added the standard deviation once to get 105 and I subtracted it once to get 95. So the number of times you add or subtract it is the z-score. So if you add the standard deviation once to the mean, it's +1. If you subtract it once from the mean, it's -1. Okay? So now let's take a look at the next one. So why am I adding 5 and subtracting 5 again? So remember, the standard deviation of 5, it's not an absolute distance. It's an average distance. So remember, what does average mean? It kind of means it's kind of, not the endpoints. All right? And also, average distance means that there are some scores that could be well beyond the average distance. Well beyond the average distance. So let's go 5 more in each direction. So 5 more from 95 is 90. 5 more from 105 is 110. Just keep adding or subtracting the standard deviation of 5. Now, what would you guess the z-scores for those are? Hopefully -2 and 2, because now I've added and subtracted the 5 2 times now. All right, so I started from the middle at 0. I added 5 once, and I added 5 a second time. I subtracted 5 once, and I subtracted 5 a second time. Now, of course, when you have very extreme outliers, in statistics, what we typically do is we go one more time, and we add and subtract the standard deviation a third time. Okay? And that really completes our number line, which will, for the most part, give us a very decent range for the data set. Okay? So those are the z-scores. Next example. Now, hopefully this is pretty easy, and I'm showing you a second example to make a very important point. So we're going to do this one really quick. So let's suppose another population has an average of 5 and a standard deviation of 1. Let's see if we can set up our two axes. So for the x's, so what do we put in the middle? We put the average of 5. And remember, we're going to go to the left and to the right 3 more units by adding and subtracting what? The standard deviation of 1. So I'm going to add 1 a few times. I'm going to subtract 1 a few times, which gives me those numbers there. What do you think the z-axis is going to be? So the mean is always the middle. So remember, the mean was 5. So what's a z-score for the mean? What is it by definition? It's 0. So we're going to put 0 here. And then when I go off to the right or to the left, it's still going to be -3, -2, -1, 0, 1, 2, and 3. Because the z-score kind of indicates the number of times you've added the standard deviation to the mean. You added it a first time, a second time, a third time. Now, what's the point here? Here it is. So the first point is that every data set has a different x-axis. So if you look at the x-axis for these two problems, you got different numbers. But however, look at the z-axes. They're exactly the same. So there's a beautiful statistical point that we can make here, is that you can use z-scores to compare any group of data that you want, because the z-scale will always be the same. So if you have a group of 100 people and a group of 10 people for the same purpose, you can compare them. They don't have to be the same size. They don't have to have the same average. They don't have to have the same standard deviation. But because every time you scale it, you're going to end up with a z-axis like these, which will go from -3 to 3. So every data set, in other words, regardless of the numbers themselves, can be measured on the same scale. Isn't that a beautiful point? All right, so now, going back to this, these z-scores are easy, 1, 2, 3. Well, what about in-betweens? What if I had a score of 102? What would that be, right? Obviously, it'd be somewhere between 0 and 1. What if I had a score of 109.1? It would be somewhere around here. So how do you convert your x values to z-scores? That's the formula here. So that calculating a z-score converts all of your data to z-scores. So for sample data, here's how you do it. The z-score is found by taking your data value x, subtracting the average x bar, and dividing by the standard deviation. For population data, it's exactly the same, but the symbols change. So same idea for population data. You still have x as your data value, subtract the average mu, divide by the standard deviation, sigma. So those are the formulas. Same exact formula for both circumstances. Here are some notes. Now, we've talked about outliers before. Here's a more accurate way of identifying outliers. So if you take your z-score and you take its absolute value, so that means just disregard any negatives. If it's more than 2, the data value is unusual, meaning it's an outlier. However, there's even more extreme circumstances. If the absolute value of the z-score is more than 3, we consider that extremely or very unusual. All right, extremely or very unusual. One other thing, it's just very standard, is that whenever you calculate a z-score, we use 2 decimal places. Okay, now you have examples to do on your NTS. So let's suppose that, and this is actually from your textbook, the average 20 to 29-year-old man is 69.2 inches tall with a standard deviation of 3 inches. Find the z-scores for two guys who are 70 inches and 60 inches tall. Interpret these z-scores as well. I don't know what is about the weather today. This rain, it's Monday night that I'm recording this. This rain is driving my voice crazy. Anyhow, the solution, starting with 70 inches. So first we start with the formula. All right, now here I'm using the population formula because this sounds like a description of all men who are 20 to 29 years of age. So that's probably a population. If you use the wrong symbols, that's okay. You're going to get the same answer, so don't worry about it. So I take the 70, which is the data value corresponding to one person, subtract the average, 69.2, divide by 3, and my z-score is 0.27. So it's somewhere between 0 and 1. How about for a guy who's 60 inches tall? Same idea. Take his score of 60, which is his height, subtract the average, divide by the standard deviation of 3. His z-score is negative 3.07. So he's like on the far left side of that z-scale. Now, how do we interpret these? So the man who is 70 inches, we would first say that he is 0.27 standard deviations above the mean. It's above because it's positive. And also there's nothing unusual about it because it's not more than 2 and it's not more than 3. The other guy, though, is 3.07 standard deviations below the mean because it's negative. And because it's more than 3, his height is very unusual. And because he's on the low end, he's very unusually short. Okay? Here's the second example. This is the baseball example that is mentioned on your NTS. So I'm going to read through it real quick. So we're going to suppose that the LA Angels, which are part of the American League, scored 773 runs in one season. The American League had a mean of 677.4 runs with a standard deviation of 51.7 runs amongst all the teams in that league. The Colorado Rockies are part of the National League, and they scored 755 runs in the same season as the Angels. The National League had a mean of 640 runs with a standard deviation of 55.9 runs. So now here's what we really want to do with z-scores. We want to compare the two teams, and remember, they're from two different leagues with different means and different standard deviations. We want to compare two teams from two completely different groups, and we want to determine which team had the relatively better seasonal runs, or the better number of seasonal runs. Okay? Now, can you take a guess which one you think is better? So you figure the Angels had 773 runs. The Rockies had slightly less, 755 runs. But that won't necessarily mean that the Angels did better than the Rockies. Watch. All right, so here's what I did. I just quickly summarized the Angels. So X is their number of runs. And then here, because we're looking at a population of leagues, all right, we're not leaving any teams out. So the mean of all the teams of the American League was this, and the standard deviation was 51.7. So ZA, or Z for Angels, again, here's our formula. Plug in the numbers that are given, compute it, and you get 1.85 for the z-score. So this group is above average. For the Rockies, again, here are their stats. All right, X is their number of runs, and then the average and standard deviation for all the teams in the National League. All right, same idea. ZR, or the z-score for the Rockies, is, so you plug in the values, just follow the formula, and you get 2.06. The Rockies are also above average. Now, their number of runs is lower than the number of runs than the Angels. Why do they have a higher z-score? Because they're from a different league. So that just means, in terms of comparing their number of runs to the average of their league, they did better than the Angels did compared to the average of their league. Okay? So in other words, the Rockies, in terms of average runs, they placed higher in the National League than the Angels placed in the American League. All right? The Rockies placed higher in their league than the Angels did in their league. All right, so comparing these, obviously the Rockies Z-score is higher, right, 2.06 versus 1.85, which we just say, again, in terms of comparing them in terms of their placement or rank, the Rockies had a relatively better season scoring runs than the LA Angels. All right, and our final part here is the empirical rule. And before I define the empirical rule, I want to point out something about graphs and how we can interpret them. So in a pie chart, all right, we know a lot about pie charts, right? It's their percentages, their probabilities that describe the categories of a particular problem. And we also know that if you add up the percentages of all the slices, you get 100%. And the percentages can also be used as probabilities. So for example, the probability of A is 25% because empirically it makes up 25% of your data set. And then similarly, just use the percents from each of the other wedges and you can get similar probabilities for those as well. We can apply that to other plots. Typically, we only see this in a pie chart because it's so common. How about on a bell curve? We can slice up a bell curve in the same way that we slice up a pie chart. For example, suppose I just randomly slice up the bell curve like this, where I have 3 wedges or sections broken up at A and B. Here's what we can say. All right, so this 10% region is to the left of A. So we can say the probability or percentage of the data that is less than A is 10%. Now I go to the 20% rule. That's everything above B. So we can say that the probability that our data set is more than B is that 20% wedge. 70% that you see in the middle there, that's between A and B. So it would look like this. The probability or the percentage of the data set X, that's between A and B, is 70%. Now one note, because you might be wondering why I didn't say less than or equal to, greater than or equal to, you can. So in a graph like this, where you're using wedges as area, it doesn't matter if you say less than A or less than or equal to A. Because what we're doing is we're measuring area in a graph, and this little line that you see here at A and the line at B, they don't have area because they have no width. So it doesn't matter if you say less than that part or less than or equal to that line. Because again, A and B, those lines, they don't have any area. So it's not going to change the 10%, the 70%, or the 20% if you say less than or equal to. It makes no difference. All right, so here's the empirical rule. So if a distribution is roughly bell-shaped, and again, the last example that I showed you, I used a bell curve purposely because the empirical rule applies to bell-shaped graphs. So then, number one, about, not exactly, but about 68% of the data will lie within one standard deviation of the mean. So remember that number line that I drew where we had z-scores of 0, 1, and -1? All right. Under a bell curve, between -1 and 1 for the z-scores, we're going to find about 68% of the data. All right. So again, between a z-score of -1 and 1, which can also be represented by this, where you go 1 standard deviation below the mean, 1 standard deviation above the mean, we'll find 68% of the data. Similarly, if we go further out to -2 and 2, we're going to have more area. So we're going to have about 95% of the data will lie within 2 standard deviations of the mean. So again, that's between a z-score of -2 and +2. Or another way of saying that is -2 standard deviations from the mean, +2 standard deviations above the mean. All right, is another way of saying that. And then for -3 and +3, we're going to find almost all of the data, but not 100% of it. All right. So here the rule is about 99.7% of the data will lie within 3 standard deviations of the mean. And again, just like above, very similar. That's between z-scores of -3 and 3. And the most important key word here is the word about, not exactly. All right, it's an estimation, which usually works very well. All right, so here's what the rule looks like on a graph. So on the bottom here, we have our z-scores. And of course, the middle there should be 0, but they have mu there. Okay, so if you look at the red here, that much of the graph, that much area, those two wedges will make up 68% of the plot. If you go out to -2 and 2, all right, so you'll have a big chunk of area that I'm circling here. So about 95% of your graph will be contained in there. And then -3 to 3, the green portion, will take up about 99.7% of the plot. Where's the other 0.3%? Well, you could have very extreme values in these little tails, these little wedges over here and over here. So there could be a little more data way out there, and that would make up your 100%. So for example, this is also on your NTS along with this problem. IQ scores. This is a good psychology problem. They have a bell-shaped distribution with a mean of 100 and a standard deviation of 15. Let's apply the empirical rule. So I'm going to use mu and sigma because typically when you talk about IQ scores, we're trying to estimate the entire population. So we'll say mu is 100 for the mean and standard deviation sigma is 15. All right, so what I'm going to do is I'm going to scratch off those things. All right, because we're going to use not z-scores, but we're just going to use the actual scores themselves. So remember, the mean is 100, so we put that in the middle. The standard deviation, that distance of 15, we're going to add 15 and subtract 15, which gives us 85 and 115. We're going to add 15 and subtract 15 again, so you get 70 and 130. And then add 15 and subtract 15 again, and you get 55 and 145. So the empirical rule has 3 statements. The first statement, we would say about 68% of the IQ scores. So notice they're going to fall between 85 and 115 in this red zone. Part 2, about 95% will fall within the blue zone here. All right, so between 70 and 130, we'll find about 95% of the data. And then the third part is the green part. Between 55 and 145, we'll find about 99.7% of the IQ scores in the data set. Simple as that. At least I hope you think it's simple. Now, we can further break down this graph kind of like a pie chart and apply or give a percentage to each of these wedges that you see here in the plot. So if you take a look at these 2 wedges in the middle, remember this corresponds to 68% of the data. So what you can do is use the fact that bell curves are symmetric. So take that 68% and divide it up into those 2 wedges. So 68 divided by 2 is 34. Okay, and then you do something similar for all the other percentages, and here's what you get. You get 13.5% will be in this wedge, 2.35% in this wedge, 0.15%, only that much in this wedge. And of course over here, it's again symmetric, so the numbers will repeat themselves. All right, so it's a different way of taking 68, 95, and 99.7 and using symmetry to break the numbers up into little wedges, just like a pie chart. It's exactly the same idea. All right, so now let's use the IQ problem on this plot here and break it down. This is also on your handout, by the way, so you can start writing on the handout or in your copybook. Okay, so here are the numbers that we used for the plot. And because there's so many numbers and so many wedges, there's a lot of things we can say here. You could probably say at least 15 or 20 things about this plot. Here are some of those. So first, just pick out any of the numbers that you see. So the first one that comes to visual here is 34%. But there's two of them there, so we could say 34% of the IQ scores are between 85 and 100. And then the other 34% is this wedge. This wedge is between 100 and 115. So we could also say 34% of the scores are between 100 and 115 as well. Let's use the 13.5s. So this wedge here is between 70 and 85, and this wedge is between 115 and 130. So therefore, we could say about 13.5% of the IQ scores are between 70 and 85, as well as 115 and 130. So how about this question? What percent of the IQ scores are greater than 115? So here's 115. What's greater than 115? Now, if there's more than one wedge, that's okay. So what do you do when there's multiple wedges and you want to know what the total is? Add them together. Right, add them together. So in order to do that, what wedges do I add up? This wedge, and this tiny wedge over here. So there's three wedges to add together. The 13.5%, 235, and 0.15, which adds up to a nice 16% exactly. What about less than 70? So find 70. Less than is anything to the left of it. So now we're going to add, there's only two wedges to the left of 70. So it's this wedge, 2.35 and 0.15. And 2.5% is the total. How about between 70 and 100? So now find that on the number line and ask yourself, how many wedges are between 70 and 100? So two wedges, right? 13.5% and 34%. Add the percents together, bam, 47.5%. Here are some other things. It's not written down, but above what score is unusual? So remember 2 standard deviations, so here's plus 2 sigma. So above that would be unusual. So above 130 is unusual. What about above 145? That's above 3 standard deviations. That's very or extremely unusual. And of course, on the opposite end, that's true as well. Below 70 is unusual. Below 55 is very unusual for IQs. All right, now our last problem here, we're going to explore the accuracy of the empirical rule. So we're using this table here from number 39 on page 145. So the first thing you want to know, well, to use the empirical rule, your data has to be bell-shaped. How do you know if it's bell-shaped? Graph it, okay? So when I graph it, it looks like this. You don't have to do that in your labs or your homework. We'll just assume it's bell-shaped, I'll tell you that. But here, when you take a look at it, it goes up and then comes back down for the most part. So this, for the most part, has a bell shape, right? Up and down. So we would say, yes, it's bell-shaped, which means the empirical rule can be used. If it's not bell-shaped, you can't use the empirical rule. All right, so next. If you plug these numbers into your calculator and do one var stat, you get the mean and standard deviation right here. So now what we're going to do to see how accurate the empirical rule is, we're going to compare the statements of the empirical rule with the actual data set. So the actual data set has a mean of 100.6 and a standard deviation of 16. So the empirical rule, step 1, would tell me that 68% of the data will be between 84.6 and 116.6. How did I get that? So remember on the number line, 100.6 would be in the middle, and then what do you do next? You're going to add 16 and you're going to subtract 16 from the average. That's how I got those numbers. Now, what about the actual data set? So now what I'm going to do is, how many numbers in my data set are between 84.6 and 116.6? So if you go through here and you count up how many are between, there's 30 numbers total, and 21 out of these 30 are between 84.6 and 116.6. What's 21 out of 30? 70%. Compare that to the empirical rule of 68%. That's pretty darn close. That's pretty accurate. There's a difference of 2%, which is a really good estimate. It's a very good estimate. Now, what's convenient about the empirical rule? Suppose your data set had 3,000 numbers. It's not going to be easy to count your data set with 3,000 numbers. Unless you know how to use computer technology and coding software, then sure, you could do it that way. All right? But when you have a very large data set, the empirical rule is going to sum it up nicely for you without having to count the data set yourself. Okay? So 70% are actually between 84.6 and 116.6 compared to 68% in the empirical rule. It's pretty good. All right, the next step, about 95% are between 68.6 and 132.16. How do you get these numbers? Well, remember, take the standard deviation of 16, add it and subtract it again to these numbers right here. So subtract 16 from the lower number, add 16 to the higher number. If you're not sure, make up one of those number lines that we did. All right, now what about the actual data? If you count up the data values in your data set that are actually between these two numbers here, 29 out of the 30 are between 68.6 and 132.16. 29 out of 30 is 96.7%. Compared to 95% in the empirical rule, again, very good estimation. Very good estimation. Are between those values. All right, and finally, the empirical rule tells us that about 99.7% of the values will be between 52.6 and 148.16. Again, add and subtract 16 from these. So subtract first and then add. Now the data set, all of the numbers are between these, which is 100%, which is, again, very close to 99.7. So again, it's a pretty good estimate. Okay, so that is it for today's lecture. Remember, you have until 5 p.m. to submit your NTS. Have a great day.